Good morning. Both of you are good. All the best. You should crack. Quickly, I will cover. Okay. So, starting from signal processing. So, if you are having any doubt, you stop me in between and I will explain. So, already all of you are aware signal is, what is signal? Signal is nothing but which is conveying some information. Okay. So, already studied in your signals and systems various types of signals. Continuous signal and discrete signal and digital signal. Okay, now I will briefly touch all these points. So now here we are discussing about discrete times LTI system. In next PPT I will explain how we are getting from continuous to discrete, discrete to digital signal. Presently I am concentrating on input signal is discrete signal. Okay, already all of you are aware of when you are passing through any system. LTI means it has to satisfy linearity property. Linearity means it has to obey superposition as well as in superposition once again you are having two parts, additivity and homogeneity. When it is satisfying these two conditions, then we say that it is satisfying superposition theorem. Okay, whenever it is satisfying superposition theorem, then the given system is linear. Okay, time invariant. When we are designing any system, always it should be linear, time invariant and stable and causal. It has to satisfy these conditions. Okay, time invariant means suppose we are buying a cell phone today. For example, if it is producing 5 decibels sound, tomorrow also irrespective of time it has to produce 5 decibels only. We want such systems irrespective of time, the output should be unique. Okay, such type of system we are designing in real time. So you are giving input. For example, you want to hear my voice. I am giving my voice signal as input. At the receiver side, Amrita wants to listen to my voice. Okay, instead of my voice, Spandan voice has transmitted and received to Amrita. She is expecting my call. Instead, she received some other call. She is not aware whose call is that one. Okay, so but we don't want such thing. Whatever we want to communicate, we have to design system such that it has to produce that only. In between, your system is transforming the given input and delivering output according to our requirement. This is discrete time, linear, time invariant system. So just now I mentioned, quickly I will go through all these things. Actually, I am using all these PPTs is ARM. Actually, I never use PPTs to teach DSP, but it is not possible to cover entire syllabus. Giving overview. Actually, in Qualcomm, they ask signal processing and image processing also. I want to touch up some of the fundamentals. Quickly, I will go through that. Okay, already you are aware of all these things. So, just now I mentioned continuous, discrete, periodic and aperiodic. Okay, already you know periodic means the same signal is repeating after certain interval of time, then we say that the given signal is periodic, otherwise no. And deterministic and random signal. Okay, my speech signal, I am unable to represent that in terms of mathematical equation. Okay, such signals we are calling as random. Already you studied the probability and random stochastic process in your second year. That is random processes. So you are unable to express or write equation for your random signal. Okay, deterministic signal means already whatever you studied in your signals and systems. Okay, for example, sin t. Okay, you are able to x of t equal to sin t. You are able to write your signal in terms of any mathematical equation. Okay, that is deterministic. Coming to energy and power, this is also very, very important parameter in our signal processing and any communications. These two things are very, very important. Okay, so why you require various measures? Already you studied in your earlier classes also. Okay, for example, I am having one pulse. Okay, I want to measure strength of this pulse. So already you studied in your school by using simple. For pulse, I want to calculate strength of the signal. Simply, I am using area concept and calculating strength of the signal. Okay, that is valid. Area concept is valid here. For example, I am having same pulse which is having positive and negative. Okay, whatever concept, area concept is valid here, but coming to here, it is giving wrong result. The area under the curve is 0. I need some other measure to measure the strength of the same signal. Okay, for that I am using the concept of energy. I will tell how you are calculating energy power. So in few seconds. Okay, now in this case for measuring strength of this signal, one pulse is nothing but it is having finite duration signal. Whenever you are having signal of finite duration signal, you are using energy to calculate strength of the signal. Okay, during this case it is valid. For instead of that, the signal, I am having another signal. My signal is extending from minus infinite to infinite. For example, you are having one periodic train of pulse. Okay, so now whatever you are having, the energy concept, if you want to apply the same thing for here, it is giving energy is equal to infinite. When you measure periodic signal, if you calculate energy of that, it is giving infinite. So I need some other measure to calculate the strength of the signal. So we are using power. So because of that one, we are having various measures. Initially area, afterwards energy, afterwards power. Okay, now I will show equations related to that one. So these are the some of the things generally we are using in signals. Based on this one, we are classifying whether signal is continuous or discrete, periodic or aperiodic, deterministic or random, energy or power. Most of the cases, all periodic signals are power signals, mostly. In some cases, neither power and nor energy, or aperiodic signals are energy signals. In general, that is the concept. Okay, now already you know this is a continuous signal representation. Okay, now from x of t is continuous signal. If you want to discretize that signal, simply you are replacing t by nt. So whenever you are replacing t by nt, so that signal now here it is continuous. Okay, this one we are calling as continuous step signal. Okay, some of the basic signal already you studied. That is the step signal. Step signal is having amplitude from 0 to infinite. Okay, here we are assuming unit step. Because of that one, it is having amplitude 1. It is continuous. When you want a discrete, what we are doing is we are replacing t by nt. Okay, so now a discrete time signal may be formed by sampling a continuous signal. Already you studied the same concept in signals and systems. Suppose what is the need for going for a discrete? Can't we do process by using analog? Why are you going? Already you studied many differences are there. Okay, one of the easiest way for going for signal is digital signal is easy to store and easy to retrieve. And if you are having any error in the transmission, you can detect and correct the errors. But you don't have such facilities in your analog systems. Okay, even though the complexity is little bit more, when you are doing analog processing, simply you are using analog system and giving input as analog, output also in analog form. Whereas in the digital case, actually all real-time signals are in continuous. Whatever signal you are capturing, whether it is temperature, whether it may be humidity or whatever my speech signal, all are in continuous form. Okay, what for we are converting into digital or discrete? For easy processing. Okay, not only processing. For example, if you take any person is suffering with some heart attack. Okay, so you want to check at what instant it has happened. You want to check the frequency. Okay, so all those things are not possible by using analog systems. So because of that one, we are going for digital. Okay, so simple. Actually here we are not explaining sampling concept. Next PPT I will explain only simply by using switch. Okay, you are passing continuous signal. Whenever switch is closed, at that instant only you will get your output. Remaining all other instants, you won't get anything. Okay, that is simple. What we are doing is in real time we are multiplying continuous signal with some switching function. generally whether it may be impulse or pulse. Afterwards you will get continuous only. So you are passing through sample and hold, is holding the same value. Okay, so afterwards that signal we are calling as discrete. Okay, if you want to transmit that discrete signal, during that time we are doing coding, converting. Suppose after doing quantization I got 5. Okay, instead of transmitting 5 I am transmitting 101. Okay, already studied in your communications. Okay, quickly I will run through. Already I mentioned the same signal is repeating after certain time. Okay, it is satisfying then periodic or not. In the digital case also the same thing. Okay, this is also one of the property of deterministic and random signals. Already I mentioned this one only. So any deterministic signal can be expressed or described by algebraic function or otherwise mathematical equation. Both are one and the same. Already I mentioned this point. Okay, now coming to energy and power. How to calculate energy and power. So this
Excuse
is
me, ma'am. Ma'am, స్క్రీన్ షేర్ చేసేటప్పుడు స్లైడ్స్ ఏం చేంజ్ చేయట్లేదా మ్యామ్? లేకపోతే
చేంజ్ చేశానమ్మా, చేంజ్ అవ్వట్లేదా మీకు?
ఒక్క నిమిషం మ్యామ్, నేను మళ్ళీ ఎగ్జిట్ అయ్యి జాయిన్ అయిపోయాను.
నేనే మళ్ళీ రీషేర్ చేస్తా ఉన్నాను.
అవ్వట్లేదు మ్యామ్, అంటే శాంప్లింగ్ రీకన్స్ట్రక్షన్ అండ్
షేర్ చేసేటప్పుడు ఒక విండో షేర్ చేశారు మ్యామ్, ఫుల్ స్క్రీన్ షేర్ చేస్తే ఈజీ. ఎస్
Previously I explained this one. This also you are unable to see this one.
ఫస్ట్ నుంచి ఏం లేకుండా.
అయ్యో. So now anyhow I am coming. I am explaining energy and power.
Yes.
Okay, now you are having this pulse. Now are you able to see my screen?
Yes ma'am.
Okay, for this pulse I am using the concept of area. Okay, whenever I am having pulse having positive and negative, during that case the energy concept is valid. Okay, the same pulse having infinite duration. Okay, my period signal is having minus infinite to infinite duration. If I use the energy concept, it is giving infinite. So I require some other measure, that is power. So because of that one, you are having energy, power and area. These three different concepts are there. Mainly we are using energy and power in all our communications. Okay, so I am you want to transmit my voice, so you want to check the strength of the signal. Okay, so by using these concepts we are measuring. Whenever it is periodic signal, energy, already you know energy equation, E equal to limit t tending to infinite integral minus t to t. Actually mod of x of t antamamma. Actually you don't know whether your signal is real signal or complex. In general we are taking mod of x of t whole square. Okay, so when you want to calculate the average power of a signal, I already mentioned why you are having two different measures. Okay, p equal to limit t tending to infinite 1 by 2t average. The value should not exceed, that's why we are calling as average 1 by 2t.
మీకు ఏ స్క్రీన్ కనిపిస్తుంది మ్యామ్?
నాకు ఎనర్జీ అండ్ పవర్ ఈక్వేషన్స్.
మాకు అది కనిపించట్లేదు. మాకు మళ్ళీ ఇందాక నోట్ ప్యాడ్ లోనే ఉన్నాను. ఇంకా
ఎందుకు అట్లా, ఎందుకు చేంజ్ అవ్వట్లా? ప్రతిసారి చేంజ్ చేయాలి, అవసరం లేదు కదా.
అంటే మీరు స్క్రీన్ షేర్ చేసినప్పుడు ఫుల్ స్క్రీన్ అని పెట్టాను మ్యామ్, విండో అని కాకుండా.
దాన్ని విండో పెట్టమన్నావు అందుకే అది పెట్టా.
లేదు మ్యామ్, ఫుల్ స్క్రీన్ పెట్టా.
Now is it okay now?
Yes ma'am, PPT షిఫ్ట్ అయ్యింది.
ఇప్పుడు
yes ma'am, PPT షిఫ్ట్ అయ్యింది.
ఇప్పుడు ఏం షిఫ్ట్ అయ్యా?
దానికి షిఫ్ట్ అవ్వలేదు మళ్ళీ.
ఇప్పుడు ఇందాక నేను రాసింది కనిపిస్తుందా?
లేదు మ్యామ్, PPT లోనే ఉంది ఇంకా.
ఎందుకు ఇది వై ఇట్ ఈస్ నాట్ షిఫ్టింగ్? యాక్చువల్లీ యూ కెన్ డూ బోత్. వాట్ హ్యాపెండ్ ఐ డోంట్ నో. ఓకే లే. నౌ ప్రెసెంట్లీ ఎనర్జీ పవర్ PPT కనిపిస్తుందా?
yes ma'am.
Okay then. Okay, so now if you want to calculate any given signal is power signal, you should have finite power. So then we say that the given signal is power and it is having energy as infinite. Okay, for energy signal, energy should be finite. Already you studied all these things. Quickly I am telling these equations. So already you know, for example, some standard signal, discrete delta impulse function or Dirac function also will call integral minus infinite to infinite delta t is equal to 1. For discrete time signal also delta n is equal to 1. Only it is existing at 0, remaining all other values, its value is simply 0. Similarly, step signal. Okay. So any signal u of t is equal to, suppose if you want to represent in terms of impulse, already we studied that one. Any signal can be expressed as sum of shifted impulses. Okay, so by using the same concept here also, your unit step signal also we are expressing in terms of impulse in the case of continuous signal, in the case of discrete signal also. Okay, so now coming to sinusoidal, x of t equal to sin omega t. In the case of discrete, I already mentioned t is replaced by nt, n capital T. Capital T is sampling period. Okay, so now in terms of complex exponential, x of you are having some complex exponential signal also, x of t equal to a e power j omega t. Okay, it is continuous signal. In terms of discrete, a e power j n omega t. So now I am not explaining all phases of all those things. Okay, so this all of you are familiar with this. In intermediate itself you have learned. Okay, if you want to calculate for any Z transform or Fourier transform or Laplace transform or any transform or any series of cos or sine, instead of taking cos signal, you have to express that in terms of exponential and you have to calculate its value, whatever it is asked, if it is asked. Okay, so it is not possible to calculate directly by using cos omega t. So you have to express whether it may be discrete or continuous. In both cases, you have to express cos or sine in terms of exponential, and afterwards you have to use appropriate equation and you have to calculate those values. Okay, so now this is coming to actually how we are converting into analog and digital. Next PPT is sampling. I will explain clearly about sampling. Okay, so now impulse response of LDA system. This is also one of the important concept. Okay, so what is response? Response means you are applying some input. Already I showed in the first slide. I am applying some system. I am having one system here. I am applying some input and calculating my output. Okay, so for example, you are applying input as xn. I want to calculate yn. So in most of the cases, you are calculating yn is equal to x of n. For example, you assume your system function as hn. Okay, yn is equal to x of n convolved with hn. So that is equal to. Are you able to see my notepad?
No.
What happened to this one? I don't know. Actually, previously I used to tell like that only. But when I am sharing, okay, once quickly I will explain that concept. Okay, even though you are expert, but I will quickly. Now, notepad is visible? New notepad
No.
is visible, Amma?
No, ma'am.
What Microsoft Teams is doing? Now?
No, ma'am.
Now is it okay?
No, ma'am. We can't see that.
Ma'am, your screen is not being shared.
Already shared, Amma. Sweta, ఇట్లా ఒకసారి ఎందుకు ఇక్కడ సతాయిస్తుంది నాకు? Actually, I want to share sometime PPT, sometime board. I'm unable to share. Why? What happened? Both down. అంటే ఒకసారి దీని మీద రా చెప్తున్నా, ఒకసారి అది చేస్తున్నా, రెండు ఒకేసారి చేయాలంటే ఎట్లా? షేర్ అది ఇదే షేర్. ఇదివరకు ఇది పెట్టి చెప్పేదాన్ని విండో. అలా కాదు, స్క్రీన్ పెట్టండి. స్క్రీన్ ఎప్పుడు కనిపిస్తుంది? కనిపిస్తుంది. ఇప్పుడు రెండు కనిపిస్తున్నాయి అమ్మా? నౌ
yes ma'am.
Okay. Okay ma, good. Okay, now actually quickly I will tell convolution equation. Most of you are making mistakes. Okay, this is my xn. Okay, and system function is hn and output is yn. When you are performing convolution, okay, that is already you know, summation k equal to minus infinite to infinite. Okay, you can take anything as first function. I am taking h of k x of n minus k. This is the convolution equation. Already all of you know this one. Or otherwise you can interchange. You can take x as first function, h as the second function. Okay, most of the cases many of you are doing mistake. Ikkada k ravala, n ravala. This output is yn. Output is yn. Your summation is varying from k equal to minus infinite to infinite. X of k, h of n minus k. First given index you have to change to dummy variable k. Okay, whichever is less complex you have to take mirror image of that one, and afterwards you are shifting with respect to n. Because of that one we are changing initially dummy variable. Here shift your axis is n. Advain andukane we are changing. This is the convolution equation. Now what is meant by this is the response. Here arbitrary you are applying some input and calculating the response of the system by using convolution. For example, I am applying my input as delta n. Okay, delta n. For example, okay, so now actually according to properties of convolution, okay, one of the property is when, okay, what can you, are you remember convolution property? Okay, so when you are applying delta n as input, for example, I am calculating, either you calculate Z transform or Fourier transform, whatever transform we are calculating, it is for delta it is 1. Okay, your system function is h of z. Okay, your output is y of z. Okay, and now when you want to calculate y of z, so this is simply x of z multiplied by h of z. Okay, now what happened? Your x of z is 1. So because of that one, what happened? Y of z is equal to h of z. So now what, if you want response, you need only in time domain. So because of that one, if you take inverse Z transform during that time, yn is equal to hn. Andukane we are calling that as impulse response. When you are applying input as impulse, whatever response is your yn. That one we are calling as impulse response. That is also same as your hn. Your hn is playing lot of key role in your filters. You are having two types of filters. Okay, instead of going front and back, here itself I will explain. Okay, based on your hn, you are having two types of filters. What are those? One is recursive, the other one is non-recursive. Okay, non-recursive is nothing but your FIR comes under non-recursive. FIR is finite impulse response. What you are having finite, hn is having finite number of samples. That name itself is indicating finite impulse response. Now just now I explained what is meant by impulse response hn. hn is having finite number of samples. Because of that one we are calling as FIR filter. The same thing we are calling as non-recursive system. Here recursive is nothing but IIR. It is having infinite, hn is having infinite number of samples. For example, I want to represent, I am not considering any coefficients at present. Suppose I want to represent my IIR system. Whenever I am computing my output of IIR system, it depends on present values of input. In addition to that, it also depends on past values of input. In addition to that, it also depends on past values of outputs also. Okay, andukane idi feedback. Okay, it is feedback system. Now similarly, suppose if you want to represent for FIR is only you are having, if you want to compute present output, it depends on xn plus only past input, not on past outputs. X of n plus x of n minus 1. Okay. So now if you calculate system function is nothing but you have to calculate h of z. H of z is equal to y of z by x of z. Already you know transfer function of any system. Already all of you studied all these things. Y of z by x of z. Okay. Now initially I am assuming all initial conditions are 0. So when initial conditions are 0, according to time shifting property, it is z power minus 1 into x of z. Okay. So once you quickly check your properties, according to that one, I am not writing one more time. Directly I am writing 1 power z power minus 1 by, okay, 1 minus, at a time you can do. I am one step minimizing. This is your transfer function of IIR filter. Suppose if you do the same thing for your FIR filter you will get it as h of z is equal to same y of z by x of z. Only you are having, what you are having, 1 plus z power minus 1. Okay. Already you studied FIR and IIR 2 units separately. So now, so quickly, whenever, all the time, the stability of the system depends on your denominator polynomial. So numerator is giving, if you equate numerator to 0, you will get zeros. If you equate denominator to poles, you will get poles. Okay, but if you see FIR filter, you don't have any denominator. So because of that one, your FIR system is always stable. But coming to IIR system, the stability depends on the poles. Okay. So always you have to check whether the given system is stable or not. Similarly, whatever you studied, you can calculate roots of your denominator polynomial whenever all the poles are lying within the unit circle. We say that the given system is stable. All the poles should be within the unit circle. Okay. If it is not satisfying that condition, we say that the system is unstable. Okay. This is the main problem with FIR filter. Why it is the problem? For example, I want to implement my IR into using a processor. Initially, I am having 4-bit processor is available. Okay. So by considering all the coefficients, I am not bothering about my float. For example, all my coefficients. Initially, I didn't mention all these coefficients. Actually, instead of one, assume it is having 1.456, etc. Here also, instead of only minus z power, it is having some coefficient 2.69, etc. Okay, I am keeping all the decimal points and checking the stability of my system. Okay, it is giving a stable system, but I don't have processor available. Only, for example, I am having 4-bit processor is available. So because of that one, I have to truncate or round. Okay. So there is no guarantee whether the given already it is previously it is stable, but now you don't know whether it is stable or not. So all the time you have to take care of this one. Okay, this is the one problem. Okay. So in FIR case, all the time it is stable, and coming to actually that also you studied in your SS. Okay, when you are designing any ideal system, okay, system కావాలంటే ఏం కావాలి, ఇది system. Already, for example, it is Hn or h of z or h of omega, whatever it may be. Suppose if it is h of omega, already you know h of omega is a complex quantity. Any system is described by two characteristics. One is mod of h of omega. Actually, I am mixing all those things. Why? Because quickly I want to complete all these concepts. Okay, you require magnitude as well as phase. Okay, if you want to describe any system, you require magnitude of that system and phase of that system. Okay, so this is SS for distortionless transmission. For example, you want to transmit my voice without disturbing. In all communication, which is important? Frequency, amplitude or phase? Which one is important, Amritavalli? Which one?
Frequency.
Very good. Frequency is important. For example, my voice frequency is 3.23 or 3.41. Exactly at the receiver side, I have to get 3.41 only. Okay. So for getting that one, I am having, actually truly speaking, when you studied that one distortionless transmission in your SS, you require, you are having system having, this is constant amplitude, this is magnitude characteristic. Okay, and nicely explained in your BP Lati. Okay, and phase should be linearly varying with respect to omega. So this also actually it has to go to 0 axis. Okay, these are the two characteristics of any ideal system. Magnitude should be constant and phase should be linearly varying with respect to omega. This is your axis is omega. Okay, but it is not practically possible. You can't use bandwidth infinite. For ideal system, you require infinite bandwidth. Practically, it is not possible. Andukane, we are going for some approximations. Already you studied. Okay, so that we are mimicking ideal characteristics. Actually, you studied Butterworth approximation. As the order is increasing, actually, what is low pass characteristic? Okay, actually, this is the low pass characteristic. Okay, it is not possible to achieve this ideal character. Ideally, you are having only two bands, pass band and stop band. You don't have any transition band. Okay, but it is not possible to design ideal systems. Because of that one, we are going for approximation. Okay, when you are designing any filter, the band between pass band and stop band should be 0 actually, ideally. But it is not possible. We are designing such that transition band should be as minimum as possible. That is our main important point in all our designing. Okay, is it okay to all of you? As the Butterworthlo chadivaru, whatever book you studied, only quickly you should be able to complete one subject in 2 hours. Okay, when they will give time, we don't know. Without wasting, you quickly read. Okay, as the order is increasing, order of the Butterworth is increasing, almost it is equal to ideal filter. Okay, that one we have studied already. So now, are you able to my PPT? PPT just confusing. Okay, good. Now what happened previously, what I did, I don't know. So this is your convolution equation, just now I mentioned. Okay, how you got impulse response I explained. Okay, so now the same thing in discrete. You will get a discrete sample, that also you are aware of that one. So this point also I mentioned. Okay, any signal can be expressed in the sum of shifted impulses. This concept also already you know. Okay, the same thing once again is explaining. So convolution. So expanding summation and substituting different values. Okay, so how we are implementing when you are implementing on processor? Actually, in all DSPs. Okay, if you take your microprocessor, only you don't have any mul instruction. If you want to multiply, shift and add. Okay, in microcontroller you are having software mul. Okay, because of that one number of clock cycles are little bit reduced. But in all DSPs you are having dedicated hardware unities available. Okay, in microprocessor we are calling that architecture as von Neumann. Here in DSPs, Harvard architecture, VLIW, very large scale, very large instruction word. Okay, so because what is the advantage of these architecture? You are having only one program memory. Actually, previously, initial von Neumann, you are having only one bus for program memory as well as data memory. Okay, here in both of them, you are having parallelly, you can execute. You are having separate program memory, separate data memory. So because of that, parallelly you can fetch data from program memory and store in data memory. Like that, you are having different address buses are available. Okay, if you take actually in fixed point 54x, okay, so in that you are having 4 buses are available. You can execute 4 instructions at a time. Whereas in 6x, okay, already you studied, you are having a dot unit. You are having 4 dot units are available and 16 registers are available. A side register and B side register. You can execute parallelly. So all those advantages are there. And one more important point is in all DSPs, you take whether when convolution or correlation or FFT or DFT or whatever equation you take, you have to multiply two things and sum many times. For supporting that one, you are having dedicated hardware, multiplier and accumulator. MAC unit is available, hardware, not software. Okay, that is the advantage of DSP. Okay, so now some of the properties already you know. Okay, these are some of the convolution properties. And correlation also important. Difference between convolution and correlation is in all real-time communications we are using correlation. Suppose I am transmitting my signal, I want to check whether it is received or not. Okay, at the we are using autocorrelation. Suppose same signal. If it is two different signal, we are calling that as cross correlation. Okay, the concept is same thing, but in the case of convolution, we are taking one signal mirror image and shifting another one. But here we are not shifting anything. We are having two signals here, one keeping constant, another one we are shifting from minus infinite to infinite. Okay, that is the only concept. Okay, suppose you are unable to calculate correlation. You can calculate correlation from your convolution also directly. Okay, instead of convolving x of n convolved with hn, that is convolution. For example, I want to find correlation of xn and hn by using convolution concept. What I have to do is xn convolved with h of minus n. Before performing convolution, you have to take minus. Okay, so this is the equation. Correlation is we are checking similarity between two signals. One is transmitted, another one is received signal. Okay, so now, so coming to DFT, I will explain DFT little bit later. Whenever it is koncham cheppali DFT ki elle mundu. Okay, so now coming to next PPT, sampling. Okay, quickly I will go through this process. Okay, already you know. Next cheppali. Okay, so now we'll go to quickly sampling. So now I already mentioned time domain, you are having continuous signal. Okay, so now if you want to represent any continuous signal in frequency domain, so that one we are calling as Fourier transform. That one we are calling as Fourier transform. Actually, what is the need to represent any continuous signal into Fourier representation? Can't we process signal in continuous domain only? What is the extra advantage? For example, I already mentioned any person is suffering with heart disease or epilepsy or whatever problem. For example, I am taking in terms of human being. Okay, so suppose if you want to check your signal, current vachindi kada, light, you want to measure whether you are getting continuous power or there is a fluctuation. So that one, that is measured in terms of frequency. So because of that one, we are converting time signal into frequency. Okay, so now when you are converting any continuous signal into frequency, already you studied properties of a Fourier transform. I am not explaining properties at present. So whenever I want to convert any continuous signal into a discrete, already you know you have to multiply that signal with switching function In that case, my switching function may be either pulse or impulse. Okay, actually, truly speaking, it is very difficult to generate impulse of zero width. That one you have studied, that concept nicely explained in TAB, Communications by TAB and Schilling. Okay, in BP Lati, he considers all the time impulse and explains, but in TAB, initially it is not possible, actually truly it is not possible to generate impulse of zero width. So because of that one, we have to consider the width delta t almost tending to 0. When you are multiplying two continuous signal with switching function, so you will get your, wherever you are having both signals are I, AND gate operation, you will get output, otherwise you won't get anything. Okay, so Fourier transform of sinusoid signal is impulse. Two impulses are existing based on this frequency. Okay, similarly, Fourier transform of train of impulses is once again impulse. Okay, I am not telling all these things. Okay, so now here in time domain you are simply multiplying these signals, but in frequency domain you have to convolve this signal and this signal. Okay, according to convolution property, when you are convolving these two signals, wherever your impulse is existing, okay, at that time you will get your original signal. See, so here I am having, this is my original signal, I am convolving this signal with impulse is existing at 0. So I got my spectrum here. Similarly, I am convolving at this place, I got the same. Okay, so similarly here, wherever your impulse is existing, you will get your original spectra. This is the concept. Okay, here in time domain simply you are multiplying, in frequency domain you are convolving. That is one of the property of convolution. Okay, so actually this concept explained in a TAB. What is meant by zero order DAC? Actually, I am unable to recollect that name. Okay, you should be very careful while selecting your low pass filter. Okay, some cases what happen, you are unable to recover back. Then we are calling as effecture effect. That one we are calling as effecture effect. Effecture effect is not discussed in BP Lati. That is only discussed in a TAB. Once you go through that definition of the effecture effect. Okay. So now this is sampling, explaining about how you have to consider reconstruction. So always according to sampling, it has to satisfy Fs, Nyquist, Fs equal to 2Fm. Fs is equal to 2Fm. That is the requirement. And T should be less than 1 by 2Fm. Okay, that is only as for your theoretical approach, we are telling Fs should minimum requirement. Minimum requirement is Fs should equal to 2Fm and jeptam. But when you want to design any real-time system, we are not considering 2 times. Generally, we are considering 6 to 8 times. Okay, if you consider more, it's good. But what happens as the sampling rate is increasing, the cost of the chip is increasing. So in all these things, you have to compromise based on our application. We have to choose your sampling rate. Okay. So so all those things when you are going for actually in ADSP, we are discussing about all those things. Okay, but the time being Fs minimum requirement is 2Fm. That one we are calling as Nyquist rate. For example, if it is not satisfying that condition, that one we are calling as aliasing effect. Because of aliasing effect, what is the problem? While transmitting, you don't have any problem, but when you are recovering back your original signal, we are unable to recover back your information. Okay, some of the high frequency component information is missing. Okay, that one only is explaining with all these diagrams. Okay, that is aliasing. Is it clear? Now, only all these diagrams is explaining with that only. So now coming to next. So already you got, actually that is not, when we are doing sampling, you won't get, directly you won't get digital signal. Okay, for example, I am sampling my continuous signal. Okay, so when I am multiplying with my switching function, for example, this is 4.1. Okay, this is 5.6 or 5.1 అనుకోండి. So now, this signal we are calling as discrete. After doing quantization, you will get even then after doing quantization also it is n-log signal only, but here we are treating that as 4. Instead of considering 4.1, we are considering that as 4, this as 5. Okay, when you want to convert digital, this is 100, this is 101. Okay, this is digital. Actually, after doing sampling, you will get discrete signal. Actually, but at your age, we are treating both the discrete and digital one and the same ani cheptamu, but both are different. Okay, coming to your DSP system, when it is n-log system, only you are having one block diagram. Okay, you are applying input n-log and output also n-log. In between, your system is processing. That's all. But whereas in digital case, one more important point I forgot to mention. Okay, sampling theorem is applicable for only band limited signal. What is meant by band limited signal? Okay, when you are taking Fourier transform for any signal. Okay, according to definition of the Fourier transform, your Fourier transform is existing from -infinite to infinite. Okay, but when we are representing in terms of previous case, only we are restricting. We are not bothering, even though it is having significant amplitude between this band, the omega m to omega m. I am having my signal is having significant amplitude from this place to this place. Even though it is having amplitude, I am not considering that points. Okay, and then what we are doing, because of that one, first diagram in your DSP or digital communication, first block diagram is anti-aliasing filter. That anti-aliasing filter is low pass filter. What it is doing, it is restricting the band. It is not allowing the frequencies above FM or WM. For that purpose, first diagram, here in this we are directly kept ADC. Generally, first you are having anti-aliasing filter, afterwards sample and hold. After sample and hold, you are passing through ADC. It is converting into discrete, and that signal we are processing into digital signal processor, and afterwards DAC. I have taken PPTs from ARM, so because of that one, they mentioned ARM Cortex. Okay, ARM Cortex processor. Okay, so actually in all real-time signals, whatever we are taking, all continuous signals, for processing them, we are converting into discrete and digital. After that, we are processing, and once again at the receiver side, if you want to listen to my voice, you have to convert into once again continuous form. Okay, so similar to that, you are having all properties, all those things. So this is continuous Fourier transform. Okay, so x of omega is integral -infinite to infinite. Actually, I will explain more easily how to remember all these things. X of t e power minus j omega dt. This is the equation to compute Fourier transform in continuous case. Okay, in the inverse case, actually, that one I will explain here itself before going further. So when you want to remember all these transforms or any equation, it is not possible to remember. You should have idea. Okay, of all the transforms, jet transform is easy. For example, I am having my signal, jet transform of x of n, okay, is equal to, actually I didn't connect my the pen tab. So this is x of z, that is equal to, mouse to rasnanke is problem. So that is -infinite to infinite xn z power minus n. Okay, all time domain signal we are converting into some other domain, whether it may be Fourier or Z, Laplace, any domain. Okay, always for that one we are calling as forward transform, except Fourier series. Remaining all we are calling as forward transforms and inverse transform. Only in Fourier series we are calling as converting time to frequency, we are calling as analysis equation. Inverse we are calling as synthesis. Okay, only difference between Fourier series and remaining other. Okay, so now for converting forward to time to some other domain, that one, for that only you will get minus. That is kal muskunna kuda inga marchipovoddu. Okay, suppose I want dtft. So already you know z is replaced by actually r e power j omega. When you want in discrete time, r is evaluated on unit circle. So during that time e power j omega t, don't bother about t. For example, actual j omega t. So in all our analysis, capital T equal to sampling period 1 anukuntam. So now you will get this is equal to, okay, that is discrete Fourier transform x of e power j omega, okay, that is equal to plus this is equal to x of omega, okay. So this is summation n equal to minus infinite to infinite xn e power minus j omega n. Okay, j omega n. So I already explained how to write magnitude characteristics and phase characteristics. You have to consider your omega is varying from 0 to 2 pi, or already that is also one of the important point. Always magnitude spectra is even and phase spectra is odd. Okay, now time is not enough to teach everything. For the timing, you remember always magnitude spectra is even, phase is odd. Already previously I shown that diagram also. Okay, so you got DTFT. This one we are calling as discrete time Fourier transform. Okay, so now here, even though you are consider x of n as discrete, when you are writing two diagrams, magnitude as well as phase, both you are getting as continuous. So what we want both discrete. So because of that one, once again we are sampling that one. So what I am doing, I am replacing what happened? My mouse right leg. Okay, so now what I am doing is I am replacing my omega by 2 pi by capital N into number of samples, in that is k. Only replacing in omega. Okay, why I am considering only 2 pi? Just now I mentioned we have to consider actually in digital. Okay, if you consider j omega n or j omega plus, if you consider omega multiples of 2 pi. Okay, already you know cos 360, cos 0, all are having same value 1. So because of that one, the same signal is repeating after this period 2 pi. So because of that one, we are considering that already you proved that property also, one of the property. So because of that one, we are considering period as 2 pi. So in discrete, we are considering period as capital N. So 2 pi we are dividing by n within the number of samples existing in that interval as k. So that is nothing but your x of k. X of k is equal to, I will take another, x of k, that is dft. Okay, that is equal to summation n equal to 0 to capital N minus 1 xn e power minus j 2 pi k small n by capital N. This is the equation 2. This is 2. Okay, like that you got all these. Okay, if it is Laplace transform also, integral minus infinite to infinite, x of t e power minus st dt. Suppose if it is Fourier transform for continuous, integral minus infinite to infinite, x of t e power minus j omega t. All forward minus. Is it clear to all of you? Like that? You should have concept. So the same thing here also. Okay, for inverse 1 by 2, whatever here you are having forward minus opposite. Okay, that is inverse Fourier transform. By using appropriate equation, you should be able to calculate. Okay, here we are not going for magnitude, all those things, phasor representation, and properties of Fourier transform also I am not touching, but okay, all of you are aware. Okay, for x of t is when you consider in time domain x of t delta t, you will get x of a, already I mentioned x of omega is 1, this one. Okay, basic signals chadivam already. Okay, some of the concepts you should remember. Okay, so you please remember some of the important duality property also, you know, for rectangular pulse. Rectangular pulse also very important. Why? Because we are using rectangular pulse only when we are shifting from Fourier series to Fourier transforms in BP Lati. Actually, when you are starting from vectors known concept, how will you say when two vectors are orthogonal to each other, when dot product is 0, you say two vectors are orthogonal to each other. The same concept applied to your signal. Okay, in that approximation, actually when two signals are orthogonal to each other, integral f1t, f2t dt should equal to 0. Okay, so now from that he mentioned approximation in BP Lathi, nicely explained. Once you open your BP Lathi, quickly go through that one. Okay, in that approximation, suppose I want to approximate one signal over the other. In that approximation, what is the error? So we have derived C12. Okay, only we are considering initially two signals. The same concept extended to n signals. Okay, from that only we are calculating mean square error. If n signals are orthogonal to each other, in that approximation, what is the error? Okay, error should be always positive. Error negative undagodu. Okay, 1 minus and under the number of terms once you open. Error should be always positive, and we have derived. Okay, two terms only we calculated. We are approximating rectangular pulse with sinusoidal signal, considering one term, two term, three term. Okay, as the number of terms are increasing, your approximation is almost equal to original signal. Okay, afterwards we are switching to trigonometric Fourier series, considering n-dimensional space. For representing a universe, minimum dimensions required is 3 dimensions. Okay, from that switching to n-dimensional space. N-dimensional space, when they are once again they are explaining concept of complete set. Complete set means, so there should not be any other dimension other than this. So because of that one, when you are considering sine and cos, okay, so when you are representing complete set, if you are not considering sine 0 is 0, no problem. Okay, so cos 0 is 1. Suppose we are excluding cos 1, your series is starting from 1 to infinite. You are excluding n equal to 0. That is not complete set. Why? Because when you are substituting n equal to 0, you are getting cos 0 as 1. Okay, that concept also nicely explained in your book once you open trigonometric. That one we are calling as trigonometric Fourier series. Okay, when actually Fourier nicely explained, initially Fourier thought all real-time signals are continuous. Okay, and he thought initially periodic. So when any signal is periodic, your Fourier series is, you can apply Fourier series and represent that signal in terms of frequency domain. After certain time Fourier form, there are some aperiodic signals also. That one, that concept nicely explained in Phillips, one of the book available in our library, Phillips. Okay, So actually, lot of when Fourier proposed that, lot of fighting happened among four scientists. Okay, finally one of the scientists, after he died, Fourier concept came into existence. Okay, when you find time, you once go through that one. Phillips nicely explained how the four scientists, when Fourier paper proposed, how they argued, all those things are mentioned. So when he believed some aperiodic signals also existing in nature, for for aperiodic signals to represent in Fourier domain, we require Fourier transform. Okay, so that also you read only BP Latik. Nicely he explained how switching happened from Fourier series to Fourier transform, only considering only this rectangular pulse. This pulse is actually, by seeing this, your periodic pulse is repeating after tau period, but he is assuming that tau is appearing after infinite duration. Okay, extending the same concept. Okay, now you read all those things. I am not explaining properties presently. Okay, those properties also important. Once you open and read convolution property we discussed. Okay, this property only we are using in sampling theorem. Okay, when you are doing sampling theorem, train of impulses. Okay, if you want to calculate train of impulses Fourier transform, once again impulse only, that impulse is separated by impulse of duration n omega s. Okay, now going to fourth module. Actually I am using directly those modules. Jet transform, actually I explained little bit. Quickly I will go through jet transform also. Okay, this is the equation of jet transform. Okay, how we derived from jet transform, Fourier transform. When you are evaluating jet transform on unit circle, your jet transform and Fourier transform are one and the same. Okay, and why you need different transforms? Can't we use Fourier transform and jet transforms? 1 second, Amma.
Ma'am, you are in mute, ma'am.
Oh, why amma? I explained lot. You should be able to tell me during that time only. Okay, so I am explaining GP formula. Have you followed GP formula?
Yes,
Amritavalli?
ma'am.
Okay. So finite GP and infinite GP. You have to see number of terms present here. When it is starting from 1 to n, you are having this a power n numerator, a power n only. If it is starting from 0, a power n plus 1. Okay. So you should have clarity about that one. So now only whatever factor you are having, you have to make it as a power n form. So here also what we did, p power n. Okay, 1 by 1 minus p. Just now I mentioned. So mod p less than 1. So now you have to calculate ROC. What is p? A z power minus 1 less than 1. ROC you have to calculate. If you calculate that one, mod z should be greater than mod a. Okay, always right-sided sequence or causal sequence, ROC is always exterior of the circle. For left-sided sequence or non-causal sequence, always ROC is interior of the circle. Okay. So this is left side sequence. Already you studied all these things. Once you go through them quickly. Okay, is it clear to all of you? Okay, even though here m equal to 1 to infinite, I am not remembering all the formulas like intermediate. Only I know one GP formula. So what I am doing, I am adding 0th term and subtracting. Okay, when I am at 0th term, what I am getting? I am getting extra 1. So because of that one, adding 1 and subtracting 1. That's all. Okay. So now, okay, the same thing once again is mentioned. The region of convergence. Okay. So region of convergence means we are evaluating the region of convergence of positive sequences outside the circle with radius mod a, and for negative sequence ROC is inside the unit circle. You can get doubt. In jet transforms, you are telling ROC with respect to cycle, but in the Laplace transform, we are discussing ROC is always strip parallel to your y-axis. Why? Can anyone tell why your ROC is in jet transform circle there strip parallel to your y-axis? Anyone? Okay, so I am not asking questions why time is not there. So because of that one, I am mentioning here r e power j omega ma. R e power j omega. Don't bother about minus or plus. You consider r some value. If you omega phasors, actually I didn't explain all phasors because of shortage of time. Omega you consider different angle, omega 0, omega pi, omega 2 pi, omega pi by 2, etc. Okay, when you are considering phasor different, it is forming contour as circle. So because of that one, we are considering contour for jet transform as circle. That is the reason. Okay. So you should be able to answer such questions when anybody is asking. Okay. So already I mentioned all these things. Okay. Region of convergence. Stability also cheppa. And one more important point is stable systems. This is also one of the important point. Stable systems have ROC that contain the unit circle. That contain unit circle. Okay, so already I mentioned this one. ROC is explaining how actually the same concept we are using in filters also, IR filters. Mainly we are using IR, actually we are designing Butterworth filter, and we are transforming all the poles which are like actually according to Laplace. The poles which are lying on the left half of S is stable. Okay, we have to map all the poles lying on the left into unit circle. Okay, the poles which are lying on the right half of S should map outside the unit circle. I will discuss that after certain time. For the time being, so you got the concept, how you got the poles, left side, right side, all those things. Okay, when it is two-sided, okay, already you know. In Oppenheim, if you open Oppenheim or Prof is nicely explained. Right side sequence, left side sequence, two-sided sequence. When you are considering two-sided sequence, the ROC is in between two circles. This is also one of the gate question. Okay, I am having two sequences, x1 and x2. Okay, so if I want to check if both sequences, there should be a common region, common ROC. Then only if you are multiplying or adding those two sequences, then only that resultant sequence is existing, otherwise no. Okay, there should be common ROC. Okay, so that is very, very important point. When you are adding two sequences or subtracting, multiplying, okay, so I am calculating my x of z by adding. I have to check where there is a common ROC or not. If there is no common ROC, that is not a Z transform is not possible. Okay, these are some of the important points related to ROC, and actually zeros are playing mainly for frequency response. Okay, and poles are deciding stability. Both are important. Okay, so you should know whenever you are designing. Actually, while designing, no problem, but when you want to implement on processor, during that time you have to take care of these things very carefully. If you are having a floating point processor, you don't have any issue, but you don't have high-end processor, but you are having limited processor. During that time, you have to take care all the time. Okay, so now I am not discussing about all these things. Properties also I am not touching. Properties all of you are expert. Only this is without initial conditions. I will check whether shifting and chopping property. Okay, one of the property previously I mentioned, according to time shifting, x of n minus m is z power minus m into x of z. If that property is available, I will explain. Okay, that one we are calling as shifting and chopping. In practice, they mentioned shifting and chopping property. So here if it is mentioned or not, I don't know. It is not there. Okay, once you check. So during that time, you have to consider initial conditions also. In this, it is not mentioned. Okay. Okay, quickly here we have few modules. I will explain all those things quickly. This is coming to actual moving average. He mentioned moving average. FIR comes under moving average. Do you know FIR filter can be represented like this? This one we are calling as direct form representation. Suppose if you want to represent your FIR equation, okay. So this is direct form representation of your FIR filter. Okay, here each and every coefficient we are considering without considering linear phase condition of FIR. Okay, here how we are doing. Actually, in adaptive delta modulation, we are using FIR filter. Okay, in many real-time applications, we are using FIR filter only. So now here, this is not here. We don't want that module. End basket. ఎవరిది?
సాధ్యం లేదు.
Okay, directly here they are going for windowing technique. Actually, when you open your FIR filters, initially you are having Fourier series method. Okay, so in that case, h of omega is given. Okay, now according to Fourier series method, what you have to do is you have to calculate Hn. Hn is inverse Fourier transform. Inverse Fourier transform just now I mentioned 1 by 2 pi. Okay, minus pi to pi h of omega e power j omega n e power j omega n d omega. By using this equation, we are calculating Hn. Okay, Hn is having infinite number of samples. So in Fourier series method, what we are doing is, for example, I want to design my FIR filter for n equal to 11 samples. N equal to 11 samples. Okay, what I am doing, even though it is having infinite number of samples, I am abruptly truncating. That one I am calling as HD of n. HD of n is having samples from minus pi to 5. You open your book, any book, you see this one. Abruptly you are truncating. After getting your HD of n, you are calculating h of z. Okay, how you are calculating h of z? From that you are writing frequency response. Okay, this is the procedure. Okay, because of abrupt truncation, you will get oscillations. Oscillations in your frequency response. That one we are calling as Gibbs oscillation or Gibbs phenomena. For avoiding that one, what we are doing is we are going for windowing technique. We are going for windowing technique. Okay, in windowing technique, what we are doing is, the procedure is same thing, but what we are doing is, instead of abruptly truncating, we are multiplying with appropriate window. Okay, so now here I am not telling ideal high pass, ideal low pass, all those things. Okay, simply what we are doing after getting that one, so we are multiplying whatever procedure I explained now, we are multiplying with window. We are having various windows. Okay, already you studied various windows. By multiplying after getting your h of n, when you are multiplying two signals, your h of n is, even though it is having minus infinite to infinite, when you are multiplying with wn window, your window is existing from minus L to L. So in when you are considering different windows, you are having different problems. Okay, so always all of your communication engineer, when you are selecting, yesterday Kansudha madam mentioned about directivity. Okay, so your main lobe width should be as minimum as possible. Okay, so you have to choose window such that window should be symmetric. As it is tending to 2 pi, amplitude should decay, and window main lobe should be as narrow as possible. Side lobe, truly speaking, side lobe level should be 0. But practically it is not possible, but you have to take care of that one. So for different windows, you are having some standard values. Okay, so we can't change that one according to our requirement. You have to choose that window. Okay, here it is not mentioned designing. Okay, that is the designing of FIR filter by using windowing technique. Okay, simply I am explaining by saying more that coming to IAR. Okay, so in IAR already I mentioned it is recursive. It is a recursive system. Okay, now if you see all realization diagrams also already you studied. Realization diagram is representing your difference equation into diagrammatic form. That one we are calling as realization diagram. Okay. So now this is direct form 1 actually. In direct form 1, for numerator delay, we are using one delay separately. For denominator also we are using one delay separately. Here see, actually in this he mixed FIR and IR together. So because of that one, this one direct form representation. Direct form IR representation. You see here B0, B1, all these are coefficients. Actually when I explained that equation, difference equation, during that time I didn't consider these coefficients. In general, we are having coefficient, numerator coefficients as well as denominator coefficients. Okay. So now this is general difference equation. In the case of FIR, only BK is existing. In the case of IR, both are existing. This summation is 0 in the case of FIR filter. Nicely explained in this slide. Okay, because of that one, I am considering these slides. Okay, already I mentioned some of the important point. Always stable, potentially unstable. Okay, filter impulse response equal to filter coefficient, number of filter coefficient done mede untadi. It is recursively, ఇది recursive system kada, FIR. So now he is explaining how to calculate all those values recursively. So now we are not calculating all those values. Okay, and now in designing of FIR filter, okay, and you may get doubt. Okay, when you are designing N-log filters. Okay, already you studied N-log filters in, I think, in your LIC. Okay, you are having actually various types of filters, but in our DSP we discussed about Butterworth and Chebyshev N-log filters. Those two filters are only used in your IR designing. Okay, when you are designing N-log filters in N-log domain only. In the case of FIR filters, you are designing your FIR filters entirely in digital domain. But in the case of IR, first you are designing N-log filters, afterwards you are transforming N-log filter into digital filter. You may get doubt. Why are you designing IR filters in N-log domain? Afterwards, what is the need to transform into digital? Okay. So simply, for simple understanding purpose, in the case of N-log domain, for example, I am having my h of s, magnitude of h of s square. Okay. So that is equal to h of s into h of minus s. I am able to separate my h of s and h of minus s. What is it? In h of s is, what is the need to separate? In the case of N-log domain, I am clearly demarcating. The poles which are lying on the left are stable. The poles which are lying on the right are unstable in S domain. But in the case of Z domain, okay, so you see, this is my Z domain. Just now I mentioned my poles are unit circle, within the unit circle, -1 to 1. All the poles, the pole may be this side or this side or this side or this side. All the poles lying within the unit circle are stable. Now I am unable to separate, like how I am doing in Z transform. In previous case, here I am unable to do that. Here I am clearly say that in previous case I am able to separate my left side and right side poles in the case of S domain. But here I am unable to do. Why? Because some poles positive side, some poles negative side. I am unable to separate these two things in the case of Z domain. Here I am clearly able to do that in the case of S domain. So now after designing my N-log filters, what I have to do is, I have to transform the poles which are lying on the left should map within the unit circle. The poles which are lying on the right should map outside the unit circle. The poles which are lying on the imaginary axis should map on the unit circle. On the unit circle. By using two techniques, actually three techniques are available. One is impulse invariant transformation, bilinear transformation. Another one is step invariant transformation. Okay. So now, by using these impulse invariant and bilinear transformation, you are able to transform the poles which are lying in the left within the unit circle, right outside the unit circle, on the imaginary map to unit circle. But in the case of impulse invariant transformation, okay, the poles, so if you consider, actually if you open, actually for student purpose I shifted to Ramesh Babu. Actually when I studied C teacher for filters at the time. Now that book is available. When I initially started at VNR, that book is not available because of student perspective. I shifted to Ramesh Babu, especially for filters. Okay, if you consider some primary strip, that is pi by 2 to pi by t. Okay, when you are considering impulse invariant transformation, one pole, actually when you are transforming one pole in S domain, always 1-to-1 mapping only. Always 1-to-1 mapping. Okay. When you are considering the primary strip minus pi by 2 to pi by t, 1-to-1 mapping is happening. But if you are considering outside this region, for example, I am having one pole here, one pole here. What happens? Those poles are mapped to, many poles are mapped to single pole in Z domain. That one we are calling as time domain aliasing. Okay, for avoiding that problem, that is the main problem of impulse invariant transformation. So because of that one, we are considering, generally we are considering to design low pass filter or band pass filter, we are using impulse invariant transformation. Okay, so during that case only 1-to-1 mapping is occurring. Designing is very easy. Okay, designing of your IR using impulse invariant transformation is very easy. How it is easy? Once you got your H of S, already you are designing your analog filter. Once you know your H of S, okay, finding inverse Laplace. Already you all of masters of inverse Laplace. Okay, always I advise single pole. Single pole means 1 by S minus 1. What is the inverse Laplace? E power minus into minus plus into plus again. So that one you compute e power t. Okay, now after getting h of t, t is replaced by nt. T is replaced by nt. You will get hn. And capital T we are assuming as most of the cases 1. You will get your hn. So you find out from hn h of z by using h of z equation. Designing a filter is easy. Okay, but you have to design your h of s. While designing your h of s, first you have to calculate the order of the Butterworth. Okay, you are having equation, you have to remember that equation. Once you got the order, you have to calculate poles. Okay, once you are calculating poles, you have to derive always when it is Butterworth, always numerator is 1, denominator based on your poles, you have to calculate those equations. Okay, presently I am not telling all those equations, the concept I am explaining. Okay, that is actually for the same specifications, Butterworth order is more compared to Chebyshev. Okay, and the poles of the Chebyshev lies on circle, the poles of Butterworth Chebyshev lies on ellipse. Okay, so because of that one, you are having many equations in designing of HFS by using Chebyshev. Okay, so you have to remember all these equations when you want to design any filter. Okay, once HFS is given, no need to remember all these equations. But you don't know whether HFS is given or not, but you should be able to explain this concept. Okay, this is designing by using impulse invariant. Okay, so actually the relation between always according to distortionless transmission I already mentioned, always your phase should be linear with respect to omega. Okay, so now I am going to bilinear transformation, one of the technique to design your IR filters, bilinear transformation. Actually that also nicely explained in Ramesh Babu. Okay, so because of nonlinear characteristics, what happened even though you are considering constant pass band, N-log filter, constant, initially you are considering magnitude. Okay, even though you are considering constant magnitude pass band N-log filter, when you are transforming into digital, your pass band is compressing. That problem we are calling as warping effect. For avoiding that problem, what we are doing is, before designing of your filter, we are doing pre-warping. We are using omega equal to 2 by t tan omega t by 2. By using this equation, we are computing pre-warping. This one we are calling as pre-warping equation. Okay, for avoiding that problem. Whatever the poles which are lying on the left should map within the unit circle, the poles lie. All these things are satisfying in BLT also. Why? Because in BLT also we are considering h of s from either Chebyshev or from Butterworth, the same thing. It has to satisfy the same condition. But because of the nonlinear, why it is becoming nonlinear? When you are designing impulse invariant, we didn't talk about nonlinearity. Why? Because we are considering for only low frequencies. For low frequencies, it is linear only. As the frequency is increasing, it is becoming non-linear. Okay. So because of that one, that problem is seen in bilinear transformation only. You don't have this in impulse invariant. It is linear only. Why? We are discussing about only low frequencies. Okay. So now in bilinear transformation, actually that also derivation is there. Okay, how you got that equation? But presently, after deriving that, once you got your h of s, for getting your h of z, simply z is replaced by z 2 by t into z minus 1 by z plus 1. Actually this there you have derivation, one derivation to get this equation. Okay, s is replaced by s, not z. S is replaced wherever s is there. Simply designing is easy, but what are the problems? You should be able to talk about that one. Okay, these are the some of the things I already mentioned, all these points. And how to, and actually when you are transforming s to z, don't by heart these equations. Actually in book is mentioning when you are transforming s pole to z pole, is mentioning with equation, but you can directly write. All of you are familiar with inverse Laplace equation. Okay, that is one step process. If you do, sometimes there is a chance of doing mistake. Okay. Andukane always I suggest you to remember single pole Laplace transform. Even though Laplace second order also easy, but coming to Z transforms, you have to remember a little bit big equation. For avoiding that one, always I suggest you single pole. When you are transforming 1 by s minus 1, this is 1 by s plus 1. That is what you will get, e power minus pt vachindi, t time domain. Okay, when you take Z transform, this factor will come. But you do by your own. Don't by heart this fact. Okay. These are the some. This also just now I mentioned 2 by t, z minus 1 by z plus 1. These are the sum of the things. Okay. And quickly some of the important point I want to touch. Image processing also. Actually design procedure, I don't want to go through that one. Design procedure. One more important point I forgot to mention before. Without using slide, I will tell. Okay, even though by using fast Fourier transform also, we are computing DFT only. But what is the need to go for FFT algorithms? Okay, so already previously I mentioned in one of these things, your DFT equation. Okay, this is your DFT equation in this slide. Okay, as the order, this capital N, as the order is increasing, as capital N is increasing, what happened? The complexity is increasing. Okay, and two more important properties of Tittle factor. Tittle factor is, actually I did introduce Tittle factor, and that one we are using from e power 2 pi by n. This one we are calling as Tittle factor or phase factor. Okay, so now because when we are evaluating DFT directly, we are not using properties of Tittle factor. But in FFT algorithms, it is having two properties. One is symmetry property, another one is periodicity property. Because of using these two properties, okay, it is able to reduce number of multiplications and additions drastically to n log n, n by 2 log n. Okay, compared to n square, n into n log, n into n minus 1. Okay, so and one more important point is how we are able to reduce. I am not explaining entire algorithm. In both cases, actually, we are having two algorithms, DIT and DIF, decimation in time and decimation in frequency. The concept is same as actually you are having XN, 8 samples. Okay, you are dividing these 8 samples into, instead of computing DFT at 8 point, we are dividing that into etc. 4, 5, 6, 7. Okay, what we are doing is we are dividing two sequences into even one side, odd one side. 4, 6. In DIT algorithm, what we are doing is you are splitting your summation into two groups. Okay, so what we have to do is we have to pick up all even samples one side and all odd samples one side. And next, actually this derivation is nicely explained in Oppenheim's small book. Okay, this is even, this is even odd. Okay, and once again it is 1, 5, this is 3, 7. Similarly, if you go further, this is 0, 4, 0, 4, etc. Okay, now this is one way of your algorithm, and here in DIT we are using one more principle, in place computation. Actually you are having butterfly. Okay, this is my A, this is B. So here you are having your Tittle factor, this is your junction point like your control system. This is A plus, for example, your Tittle factor is omega nk. This is A plus B into omega nk. Okay, similarly, this is A minus B into omega nk. Okay, this is the entire concept. And what happened initially, you are applying, you are having multiple stages. Once you are applying input here, you will get your output here. Okay, for next stage, you don't require these inputs. Okay, what we are doing is, we are storing these inputs, these output in place of previous input. So because of that one, we are able to reduce memory locations. That one we are calling as in place computation. In place of previous inputs, we are storing present outputs. That one we are calling as in place computation. And one more important point is bit reversal. Bit reversal, if you see here, bit reversal means, for example, 0, 0, this is natural order, 0, 1, okay, 0, 1, 0, only I will write a few. Okay, this is your last row. If you arrange bit reversal, what happened? Once again 0, 0, this is 1, 0. Okay, this is same thing, this is 1, 1, 0, this is 0, 0, 1. Now if you carefully observe, this is 0, 0 is 0 only, 0. 0, 0, 1 is in bit reversal order 1, 0, this is 4. This is 0, 1, 0 is 2, here also 2. Now in 0, 1, 1, this is 6. That is all last row is in bit reversal order. We are using bit reversal order also. Why? If you are applying inputs natural order, we are taking outputs in bit reversal, or if you are applying input bit reversal, we are considering output in natural order. What is the need? What happens if you are not considering like that? Okay, so actually that is nicely explained in practice. Okay, if you are not using both, if you want natural order, you require 4n memory locations. If you use one bit reversal and one natural order, during that time you require 2n memory locations. When you actually if you want to design chip, memory also very crucial. Okay, you are saving 2n memory locations. As the memory is less, the cost of the chip is becoming less. So because of that one, all these points are very, very important. This is solving problem is very easy, but this is the concept. Okay, so in DIF, actually in DIF same as your FIR logic only. Okay, FIR linear phase, initially you are having 4 derivations. What? Initially you are having the same equation only, DFT equation. Okay, DFT equation, what you are having DFT equation, previously I showed in the same equation, DFT equation. What I am doing is, I have to split my summation into, for example, even I am having odd summation. Okay, what I am doing, my odd summation I am splitting into, where is that? I am unable to track. For example, I am having 7 samples. Okay, in that 7 samples, okay, I am splitting that into first 3 as one group, first 3 samples as one group, center term 1, last 3 samples as 1. Okay, now you have to modify your summation. First one I am not changing, second summation I am modifying. How I am modifying? I already mentioned my FIR filter is satisfying linearity and symmetry condition. What is meant by symmetry? Symmetry is h of n is equal to h of capital n minus 1 minus n. Okay, in second summation you substitute this factor in place of h of n and modify that equation. Okay, so now simple mathematical manipulation, that's all, nothing else. After doing that one, you will get one equation. So now you apply what happened, my k is even. In DIT first we are dividing into even odd. In DIF we are not doing that initially even odd. First we are splitting summation into based on even samples or odd samples. Now here I am considering odd samples. Because of that one, first 3 one group, center term 1 and last 3 as another group. After that, for second summation I am imposing the condition, symmetry condition. Okay, and modifying my summation, and after getting simplification I am applying what happened, my k is even and what happened, my k is odd. Okay, k is odd, 2k plus 1. Okay, so the algorithm is simple, but only if you want to understand, even though you studied in your BTech or not, you refer only for these algorithms. Okay, up to single point. Enduku, why I am mentioning Oppenheim means in ProACIS also, in any book it is explained nicely, up to single point nicely explained by Oppenheim. Why? Because when you are solving problem, okay, n by 2, n2, n by 2, n by 2. Initially, first we are considering tittle factor 0, 1, 2, 3. For example, 8 point. Afterwards, we are considering 0, 2. You may get doubt why we are considering 0, 2. Why not 0, 1? Clarity ravalante, you have to read only Oppenheim. Nicely explained. ఎందుకంటే అక్కడ ఆల్రెడీ ఈవెన్ శాంపుల్స్ ఉన్నాయి. ఈవెన్లో you are substituting 0, 1. When you are substituting 0, you will get omega 0. You are substituting 1, you will get omega 2. Anduko I am asking you once, if you find time, not only now, whoever is aiming for higher studies, MS, you should have clarity of all these things. Okay, so this is your butterfly. Actually, Ramesh Babu arrow ikkada pettaru. Actually, many times I gave feedback, but they didn't correct it. Okay, so now this is junction point. So for up, a plus b only. You no need to multiply for up. Okay, for down, after subtracting a minus b, you have to multiply with your tittle factor omega n. This one you are multiplying. Okay, ikkada better ankondi. According to our control system, this also should be multiplied. But we are not multiplying. Because of that one, arrow should be here and this tittle factor should be mentioned here. Okay, this is brief about DSP. Okay, actually little bit image processing also required, and I have one image processing PPT. Once I will quickly run through that. You want to listen, Amma? Okay, quickly, without wasting much time, quickly go through that one. Okay, wherever you are having any issue, please discuss with someone. Okay, you are having very less time. You should brush up all communications subjects, DSP, image processing mainly. Okay, because of that one, we scheduled tomorrow also. Josna madam, networking, some fundamentals also required. Okay, you should crack. So first time they are coming to our campus. So please concentrate on that, so that you should get opportunity to join quickly. I will tell image processing. I don't take much time. Okay, I will share. Actually, this is a old PPT. Quickly, I will run through the actual compression only. This is compression PPT, not this one. Introduction to DSP. Okay, the processing of image processing also same as DSP. Okay, so even though you are having 2D convolution, all these things now available, but okay, suppose if you want to do, suppose you want to write algorithm. Okay, we are not computing at a time 2D transform. For example, if you want to write C programming. Okay, introduction, image fundamentals. Quickly I will run through that. Already you know all this no, I don't want to take much time. This is also same concept. Actually, previously we are having cameras, analog cameras. During that time, whatever process we are doing for digital communication, the same process we have to do. Now by using, we are having digital cameras. Okay, so the entire block diagram is same as your digital communication. Okay, during such case we are giving signal, here we are giving image, that's all. Okay, a picture is worth of 1,000 words. Instead of telling story, now that story I don't want to tell. So for image processing, you are applying image processing, you will get output better quality. You are having different types. Only I want to tell some of the concepts. Okay, already you know electromagnetic spectrum. Maybe Sudha mentioned about the spectrum. Okay, in image processing, entire your EM spectrum. Okay, now in medical field, actually in medical field, most of the things are used. So quickly we'll see that one. Okay, EM spectrum, you are having various applications. This is in medical. Gamma ray imaging. Now I am not discussing about that one. Simply I am quickly X-ray imaging. For example, if you want to check whether your PCB is in good condition or not after soldering. So it is not possible to check by using your eyes. Okay, scanning. Okay, all this comes under X-ray, X band. Now ultraviolet band. Okay, ultraviolet band also lithography. Lithography is when you are doing PCB. So that process we are calling as lithography. Okay, and in addition to that one, biological imaging, astronomical observation also we are using ultraviolet band. Now visible and infrared band. Okay, so this is also micro inspection, material inspection and microprocessor. So some of the application where we are using this one. Remote sensing also we are using the same infrared band. Weather, remote sensing. Okay, and now this is also one of the many applications. Now you want to check your circuit. Okay, whether tablet is filled or not. Automation. Now everyone is talking about automation. So now, for example, you want to fill the drug 1 ml. Instead of 1 ml, if you are filling 1.1 also, 1.001 also danger. Okay, so it is not possible by human intervention. So by using your image processing various techniques, you can automate the process. This is a microwave band. Already all of your experts, microwave band. So you are having many applications. Radio band. This is also MRI scanning. MRI. Acoustic imaging. Acoustic imaging actually mainly used in, suppose if you want to dig a well. Okay, when I am young, they used to do manually. Now they are calling NGRI, that is available at Tarnak. They will call, they will tell whether water is available at that place or not. Now in seas, mineral soil, so they are finding some signals, they are transmitting and receiving back. Based on that one, they are detecting whether the water is available or all those things comes under acoustic signal processing. Okay, now ultrasound imaging. Okay, so before born only, if you want to check baby health, okay, during that case we are taking ultrasound imaging. Many applications like that you are having. So for each and every band you are having n number of applications. Okay, so entire image processing is divided into 3 levels. Low level, input and outputs are images. Mid level, okay, suppose if you take segmentation, one of the technique in process that is used in segmentation, actually instead of transmitting my interface, what I am doing is I am dividing into different regions. That one I am segmenting, and afterwards representation schemes, whatever I am segmenting, my computer should be able to recognize. Okay, and that one I am transmitting. That one, that here mid level is input image, output is not image. High level is here you are doing some analysis on your image also. This is quickly about your image processing block diagram. First, you are acquiring image. Okay, now you can acquire by using camera, photo frame grabbers or scanners. By using appropriate, you are acquiring image. After acquiring image, there is a lot of noise is corrupting your image. For example, I am not a good photographer. Whenever I am taking photo by using my cell phone, there is a shake. Okay, that one we are calling as noise. Okay, we have to eliminate noise. Okay, or otherwise, for example, I am having image, any person is suffering with some brain tumor. Okay, even though I am capturing entire brain, my aim is I have to enhance. You are having enhancement techniques. Have you taken image processing as elective? Any one of you? Amma, image processing elective తీసుకున్నారా లేదా? Spandana? Amrutavalli?
No, ma'am.
Even though no, also no problem. Quickly I will tell only, without much trouble. Quickly, within 5 minutes I will give overview. Okay, so enhancement, you are having two types of enhancement techniques. One is spatial domain, another one is frequency domain. In frequency domain, same as what we are doing convolution Fourier transform, like that. In spatial domain, what we are doing is we are doing the operation on each pixel. What is meant by pixel? Actually, image is represented in two-dimensional. When you want to describe any two-dimensional object, we require matrix. Okay, so you studied matrix. Matrix element ni element antam akkada. Ikkada matrix element ni pixel antam. Pixel, picture element. So okay, how we are able to see any object, some light is falling on that object and reflecting back. Based on that one, we are saying that is pen, that is book. By using the same principle, here also we are able to identify that object. Okay, after identifying that object, we are able to represent that in terms of matrix. Okay, if intensity is more, then we are saying that it is more means intensity pixel value is more. If it is less, the pixel value is less. I will tell after few slides. It is there. I will explain that one. Mainly, we are doing operation on each pixel, that is spatial domain enhancement. Mainly two types: frequency domain and spatial domain. Image restoration. In image restoration, mainly image is degraded. Degraded means some distortion is there. By using some mathematical filters, Bilinear filter, least mean square filter, inverse filter. Okay, we are restoring the image. Okay, all those things comes under image restoration. Actually, color image processing, actually now you don't have in your syllabus, but when you are capturing any image, you are having RGB. Okay, each is 8-bit. Okay, altogether you require 24 bits. Okay, the memory requirement is very high. Instead of processing that in RGB form, we are changing color formats. We are having various color formats. Okay, so we are you have appropriate techniques to do that one. Now coming to wavelet and multi-resolution analysis. Actually, I didn't tell about what is significance of wavelet and multi-resolution. Quickly with one sentence I will explain. Okay, I already previously explained any person who is suffering with heart attack. Now 10 minutes back heart attack happened. Okay, so when you are using your time domain approach, if you are capturing time domain signal, only it is giving time information. If you are capturing frequency domain, it is giving frequency information. But I require both at a time. By using your time domain and frequency domain, it is not possible. Okay, so for that purpose, we are switching to wavelet transform. Actually, in between you are having short-term Fourier transform. It is also having some problem. Because of that one, we are going for wavelet transform. Okay, next one is afterwards compression. Already you studied compression in your communications also. What is the need for compression? Bandwidth. We don't have bandwidth freedom. We are having restriction in bandwidth. We should be able to transmit more information by using the same bandwidth. You have to compress the signal at the transmitter side, and once again you have to recover back to the original signal at the receiver side. We are having various compression techniques, and segmentation also I briefly mentioned. So for after segmenting, you are having some representation schemes. You have to represent your segmented object into representation, and afterwards it has to recognize whatever you are representing. Okay, this is entire image processing. So just I will tell suppose enhancement. Okay, this is your object image. After doing enhancement, see the clarity of the image. Okay, image restoration. This is degraded. When you are applying some filters, you are able to restore. And color image processing. So color image processing and compression also you are having. Just actually each one is 1 unit. Time is not sufficient. Only I want to show. Okay. Okay, when image is represented as, this is video. Only image is f of x comma y. When it is video, t is also there. What is the difference between video and image? Okay, when you are capturing any image or video, okay, video is, for example, some systems 25 frames per second, in some systems 30 frames per second. One frame is nothing but your image. One frame is still image anamata. Okay, types of image manaki anni avasarunda. Okay, now this is f of xy. This quadrant we are representing image in like this, f of x comma y. Okay, rows and columns already I mentioned. Matrix element. Okay, we are calling this brightness values. Brightness values we are calling as gray level. Okay, so now number of gray levels. For example, this is your image. For example, I am using 8 bits to represent my image. My pixel values varies from 0 to 255. If it is more white 255, it is dark 0 in between some values. Okay, this for example I am using n by n. My matrix rows by columns as n by n size. Okay, this is representation of my image. Okay, so now, so already I mentioned f of xy is I of xy into r of xy. How we are able to identify your object, already you studied in your intermediate. The same principle here also. Always your illumination should be in between 0 and infinite. Reflectance should be 0 and 1. And gray level I already mentioned. Okay, L mean to L max, generally 0 to 255, 0 to 0 and for example if it is 8 bit, 255. Okay, 0 is black, L is white. Just now I mentioned. Okay, for example, if you want to store any image, why you require compression? As resolution is high, it is good, no doubt. Okay, but we are having, your memory depends on this one only. If you want to store one image, for example, I am using 8-bit image. Okay, 8-bit means 2 cube. L is equal to 2 cube. L is number of gray levels. Number of gray levels required. Okay. So now number of bits used. For example, I am using m by n image. Number of storage bits required to store one image. M into n into k. Okay. As it is increasing, the memory is increasing. You can't use whatever you want. Okay. There is a restriction. So now nicely explained in Gonjali's book by considering what is the problem. Here keeping number of bits constant, reducing resolution. As it goes on reducing resolution, you are unable to identify the object clearly. That problem we are calling as checkerboard effect. Okay, the same problem with gray levels also. Keeping resolution as constant, reducing number of gray levels. During that case also you are getting problem. Okay. So sampling all those things, you know. Okay. Pixel relation also. Pixel ardhamaindi kadamma. Okay, this is brief about image processing. Okay, you should be able to talk about even though you are not aware. Okay, the processing, even though it is 2D convolution, everything is there. The same thing. Okay, once you are capturing image, you have to do pre-processing. In pre-processing, some of the Fourier transforms, actually for image, mainly we are using discrete cosine transform. Okay, even though you are having FFT, Walsh transform, like that you are having various transforms are there. Of all, discrete cosine transform is good for your image processing applications. Okay, after pre-processing, okay, based on your applications, you have to choose. For example, you want to find out your tumor. During that case, we are using enhancement. Okay, after enhancing, only you have to compress your information. For example, after enhancing, you have to transmit your image to rural. I am at rural village. I want to transmit that information to city. During that case, you have to compress. You are having various compression algorithms are there. Okay, so here you are having arithmetic coding. You are having similar to your Hoffman coding. You are having some other techniques in image processing. Okay, in digital communication, you studied about Shannon-Fano coding and Hoffman coding. In addition to that, here you are having arithmetic coding. Okay, that these two codings, all these codings comes under source coding. Okay, coding la two types unnayamma, source coding and channel coding. Source coding is in your hand, channel coding is not in your hand. You can't transmit along the channel. Okay, source coding, by using appropriate technique, you are reducing number of bits. Actually, in channel coding, you are increasing number of bits. You should be able to difference these two things when you are attending your Qualcomm. They may ask what is the difference between channel. Okay, source coding, mainly you are doing actually in digital communication, first block diagram is source coding. Once you got your signal, after converting into digital, you are doing coding. Okay, in that we are using Hoffman coding, Shannon-Fano coding. Okay, digital communication image processing like you are having arithmetic, okay, LJW coding, like that you are having many coding techniques are there to reduce at the source level. Okay, channel coding lo cyclic coding IE comes under block codes, convolution codes, Alice codes, IE channel coding lo. Don't mix these two things. That is very important. Okay, please open up and you should be able to talk about channel coding and source coding. Okay, only 1 minute type in. Amma, that is brief about image processing and DSP. Okay, quickly you refer to any book. Okay, please find out. Actually, all of you, some of you missed. Vivek inputs are very valuable. If you are having any issues, please discuss with him so that all of you should be able to crack. All the best to all of you. Thank you. I am leaving the session. Okay. I think some of the fundamentals I am able to, already we are master, but because of less time, I want to